So I present you as a representative of the University of South Brittany, work done in a research team of this university, whose objective is to complement the industrial design flow with a set of security services in order to validate security requirements of products, security requirements done at early stage from risk analysis of these products. I will focus in this presentation on two of the security services. The first one is to propose a service that offers the capability to work in a collaborative way, in the same way as the team for Capella. The difference is that we offer the capability to work, to get access of the stakeholder to the elements up to a particular level of confidentiality with an implicit assignment of a level of confidentiality for each element of the modeling elements of the modelings, with a strong protection in terms of control access of these elements. The second security services presented is the capability to annotate and enrich the modeling with information related to security requirements, and with the capability of analysis of these annotations of the announcements of these modelings, with the capability to evaluate the compliancy of the system design at physical level with respect to the security requirements. The second kind of features offer this automatic code generation in terms of ciphering, deciphering, to complement the design software done in order to validate security requirements along with operational requirements. So now I focus on the first of this service, which is model-based system engineering confidentiality management. So I take a few minutes on the problem statement some of you know very well. But in fact, we are focusing on this service on particular systems, which are critical systems or critical complex systems, on which the specification information provided by the customer contains very critical part of specification in terms of confidentiality. So then the industrials that has to realize the system has to protect the access of these parts of specification only to the people who have the right to know, who have the right to have the access to this part of information. This has a strong impact, in fact, in terms of the flows that has been chosen for the realization of the systems. And most of the time, it is a documentation-driven process, because it is very easy to separate the initial sets of specifications on particular sets with an assignment of a level of confidentiality to each of these sets, with a control access to this information, on also refinements of information of these specifications, on specification, on design documents of systems and subsystems. On such process, it is known that it creates a lot of duplications of information related to the versions, related to the subsystem, related to the customers, with a lot of documentation with traceability of requirements, with a very strong effort that has to be done on the synchronization of all these documents to be correspond to the same set of initial requirements in the referentials. So this is a very known issue on this kind of processing. That's why industrial move from the document-driven process to the modeling-driven process. So in this driven process, all the stakeholders are sharing the same sets of modelings. Then if one of the stakeholders is modifying one element of the modelings, all the other ones are notified of this modification. Then we guarantee the synchronization and working on the same artifacts of system specification and designs. This is a very known advantage, in fact, of this model-based system engineering. So, which is a consistency. Of course, also, as it was said, the on-the-fly change information notification is one advantage of this process. And also, the use of the same syntax on the same related semantics of the elements on the same modeling language has some advantage, is one of these advantages which prevents from ambiguous notations. These processing has some drawbacks. The first one is the reluctance to change of system engineering teams that are used to using documentation-based processing because they have to change their mind to use different processes and tools. And they have to wear, so they may feel to wear also straitjacket imposed by modeling, not using their own particular notations. But as these modeling languages are defined by system experts, they are supposed to have all the information needed to design and specify their systems using these modeling languages. So these are drawbacks, but not sufficient drawbacks to prevent from this moving from the documentation to model-based system engineering. But there is one which remains, in fact, which is confidentiality management, which is illustrated in this extract of modeling. I took it from the level crossing traffic control. You may find it from mbse-capella.org. So I complement this extract of modelings with an element that was generated from a risk analysis, which is a threat scenario identified, the potential attack from the threat agent from outside. So this may provide some information in terms of vulnerability of the system. Then this means that this information is confidential. So it has not to be disclosed to anyone, which means that, for example, the operational designer that has to design the system related to the operational requirements does not have to have access to this kind of information. Just working here on the part in blue and green, and have no information on these red parts. In the opposite, the security manager needs to have access on this part related to the operational design or specification of the system, but doesn't have to modify it because it's not his or her job. And also, if he or her would have the access in the right of this part, might integrate and enter some confidential information with it, which is not wished, which is forbidden, in fact. But the security manager needs to have the capability to enrich this modeling with particular information related to security information that has to be indicated in this modeling. So we need to propose a process, tools, framework in order to have the capability to work with particular control access with different stakeholders on the same modelings, with some access in read-write, on some access to up to a particular level of confidentiality of information. That is what we propose to present as a solution in the next slides. First, I present a set of criteria that I want to validate in order to be possible to be used in an industrial context. The first one is, of course, linked to confidentiality, as I presented before. Integrity here is related to the access or not access to the information, or access in read or write or read-only, as I presented before. The third element on the first line is related to consistency. I don't want to have multiple copies of the modeling with complex merge between modelings, but to have as most as possible only one with a clear definition on how to work on a single modelings. No leak, of course, of elements of high level of confidentiality to people who have control access only up to a lower level of confidentiality. We want to go further in terms of confidentiality protection of the elements, in terms of storage confidentiality. So elements of different confidentiality level are stored in different memory parts with a separate control access also. We consider it is not of the responsibility of the people to label by themselves the level of confidentiality of the elements on the modelings. No, so we want to propose an automatic labeling of this information. As of course the specification and design of systems are done by iterations, we want the solution to be compliant with the iterative design flow. And finally, we do not make any assumptions on the meta models of the modeling language. So it can be applicable to Capella meta model, but also any other kind of meta model of languages which offer different level of confidentiality of the elements that are designed, in fact. So I present the solution in this single slide with two main ideas, in fact. The first idea is the separation in enclave with a particular access control. One enclave is each enclave is related to a particular level of confidentiality. So the level of confidentiality is carried by the enclave. The second idea is the application of the known security principles defined by Bell and Lapadula. The first one is called a simple security, which is no read up. So in this example, someone that has access to the operational part of the modeling, the blue part here in the figure, does not have the capability to read elements that are defined in the security enclave here in red. The second one is the star security. It has here the security manager do not have the possibility to write anything on the operational enclave. The other element that is added on this proposal, it has when there is a move of the modeling from one enclave to one another, it is always from a lower level of confidentiality to a higher level. All the elements that were in read-write are set to read only, in fact, in the higher enclave. So implicitly, an element, if is of a particular level of confidentiality, if it is set in read-write in the enclave, and is at the level of the corresponding enclave on which the write is of read-write. So what is presented there should satisfy most of the criteria. There is still one that has to be satisfied, one of the major ones, which is the iterative flow compliancy. That is what I show in the next slide, the description. So we will have some iterations from one enclave to one another that have moved, and from one to the other, of course, there are some enrichment of this modeling with security information from modeling taken from the operational flow. So in the next iteration, we will have a new modeling with some element added, some element suppressed potentially. So we need to process consistency analysis in order to integrate what has been added in the previous iteration with the new one at the security level. This should not cause issues generally because from different level of confidentiality, generally the interfaces are well defined and should not be modified all the time, but that may arrive. If it arrives, we have two solutions. The first one is the refactoring of the elements that has to be added. The second one is to define a clear process integrating security managers in order to provide some information to the operational enclave there, in order to modify the model that has to be sent in the next iterations. In fact, we propose, we go deeper in details on this consistency analysis in the next slide, because we take advantage of the fact that the models that are sent, the .capella file, like the XML AIRD files in Capella, are XML3-based model, and they are set on read-only, which means that the only potential activities that can be done in the higher enclave is to add some elements on these XML3 file, tree models that can be modified. So it is attached in the list, in fact, or also with references with beacons, but these beacons can be modified. So it's quite easy to define the points of attachment on the beacons with references. And from one iteration to one another, we may have a look and detect if these beacons are still existing or not. If they are still existing, we can create a structural integration of the modifications, as it's quite easy to define the particular points that of the beacons that are missing that will help either on the refactoring or on the modification on the lower enclave modelings. So, and the next, I present this in one example, which is not, I think, the meta model of Capella, but it is a meta model which is quite close. In fact, what I presented is applicable on modeling, but also meta modelings. Here we have a meta model. The operational part is in blue. The part related to security is in white. And we focus on the part which are bordered in purple. So we may describe the operational and security parts on two enclaves as this. This part is a part of the meta model that allows the capability to describe scenarios. So in the one of operational parts in left, in fact, it is possible to describe operational scenarios with the meta model. And in the right part, so it moves from read-write to read-only on this part. We add on another class which offers the capability to express security incidents as scenarios. This is shown in the next slide because we have meta models, but also instances of these meta models, which are the models here, some particular scenarios. So I describe an operational scenario in the operational part, and in the security part, we may also have the capability to express security incident as scenarios, as instances of this extended version of meta model. So you may say this seems to be very interesting, but I already use Capella. I have my own modelings. I want to use such features because it's interesting to separate with the level of confidentiality the access of my modelings, but I do not want to break anything and to create new feature and to have to redesign from scratch everything. In fact, it shall not be the case because all the elements needed to integrate this is already existing, in fact, in Capella, but also in all the tools that offer collaborative capabilities. Because in Capella, for example, in Team for Capella, if one of the stakeholders is working on particular parts of the modelings, these parts are set to read-only, and it is realized when the stakeholder finished to work on this part. On the other elements, only have the capability to read this part, which is modified with the pair stakeholder, but can't modify, but there's the possibility to work on the other parts of the modelings. So the idea, as I need these capabilities to get in read or write, is to define, in fact, when the models is sent from one enclave to one another, to create a factice user that gets in red all the elements that were in the lower part of the operational part of the modelings. Then the other stakeholder has only the capabilities to enrich with new elements, which is in fact what we want. Okay, so in fact, with what you already have on your modelings, if you want to add some confidentiality elements and integrate them with the control access, you can do it. So now I presented a set of criteria. In fact, they are all validated in terms of confidentiality, integrity, consistency, no leak, storage, of course, because it's stored in the enclave. The labeling is implicit related to the creation of the elements in the enclave. The iterative design flow compliance, I showed it. Genericity of the solution. I never talked about particularities in terms of meta models. And finally, that was not expected before, but it is offered, in fact. You have a smooth modeling tools integration. So as now we have the capability to separate elements with a particular control access to the elements of confidentiality, the next step is to integrate confidential elements on models, on meta models, and to work with them, and to propose some kind of analysis related to what is confidential, which are elements related to the auto risk analysis. This is what is presented in the next security service presented in this presentation. So as for the first one, I present a few elements of the problem statement. Here we have a kind of system design of a system which is composed on subsystems which are composed, integrated within. And what we want to validate is an operational context which will be validated with the operational scenarios that will be executed on this global system. To do that, we compose it with subsystems which are a mapping of behavior descriptions as data flows, which are functional chains in Capella, which are mapped in the part of models of platform. In fact, these tools are well tooled generally to validate behaviors with a lot of help because it is integrated within the modeling tools with automatic scenario generation on skeletons, on documentation, and so on. But for example, here, this example is a very schematic description of communication systems. We may suppose that it is critical information that is sent, and potentially, if we use civil protocols for the communication, if we replace one of the terminal with a mobile phone, potentially it may work. But surely, the security of transmission of the information will not be satisfied, and that is not really present in this modeling. So what would be good, what is important is to validate by the security analysis the protection, in particular in terms of confidentiality, but also in terms of integrity of the data described in the functional chains. And this is currently lacking in the information provided at system level. So what we propose for this complex critical system is to, as it is considered as a weak tool, to enrich the modeling with information and to propose two kinds of exploitation. The first one is to analyze the compliance of the system with a choice done already at the design level on the physical view of the modelings. And also the capability to automatically generate the code related to these security requirements, to automatically have a link from these requirements to the validation, taking into account the modeling done at system level. Okay, so the first step that has to be done, it is called elicitation. It is to define the elements that has to be integrated by annotations on the current modeling at physical view from this schematic description at physical view of a communication there between two radio equipments. The first element that has to be added in terms of annotation is actions on the data on the functional chains. That can be a function creation. So the data is created. When it is created, I have to know it is confidential, sensitive information or not. So I will assign a confidentiality level to this data being created. And also the type in terms of actions on the data, which can be a function read. I can have access to the data, but it will not be modified. Function transit, it won't be modified, and I do not have to have access to it. So, for example, it can be ciphered. Function storage, which can be read or transit, but the the particularities it is memorized in a persistent way in the component on which it is deployed. On function right, the data is modified. So these functions are deployed in physical components, and some of these components may have the capability to offer some what I would call platform services in terms of ciphering and deciphering and ciphering related to a level of confidentiality of data. We won't use the same ciphering with respect to the level of confidentiality. These components may be protected from thread action of entering within to process some kind of compromission of these components. So with some protection with a level of confidentiality, C1, C2, or no protection at all. One other element, we may have different functional chain going through the same component. So we may have some contamination from one flow to one another. So we have to define some policies of the level of confidentiality that have to be set to the data going out this component related to a functional chain. And we propose to define two kinds of policies. The one is called maximum, which is the maximum of level of confidentiality that can be entered in the component. The second one, it is an analogy of secret and very secret policies. It is a fixed defined level of confidentiality for any elements going out of these components. So you have in the left part what you know as what you have in your own physical view. And with the annotations, we have what is presented in the right part. This has been designed on the demonstrator, on a proof of concept. And to that, we have as entry some Capella files. We do not use these colors to distinguish. It is just to give some elements, graphical elements. But we use the summary fields in order to annotate the modeling. And we interpret the information. And we have the information related to a component is presented in terms of confidentiality protection, in terms of the policy that has been applied on this component, and also the existence or not of capability to cipher and decipher the information. This is for the physical elements description, annotations. So not so much annotations. The other elements of annotation is related to the functional chain. So we use the particular diagrams of functional chain at physical level. And we indicate the kind of action that is done on the data, either a creation with a level of confidentiality set to the data being created, or just in use write or read or in motion related to the action to the data for the other functions. Okay. So in fact, to do that, we have an underlying modeling of functional chain with this information added. I called it secured functional chain. So you find the functional chain. It is colored with the type of function in terms of creation, write, read, and transit. And when it is a creation, we indicate the data sensitivity set at creation. And as these functions are deployed in components, we indicate information related to these components, which is the enclave protection, the capability to cipher or decipher, and also the kind of policy that is applied on these components. So this is a big picture. So we have already seen the number 1, number 2, number 3, and in the number 4, we process some extraction of this information in terms of security functional chain, and we do some analysis on it in order to proceed to some security directives in the case that there's some lacking of protection, for example, of the functional chains. And also, finally, security code. So we suppose that we have validation operational one. We may automatically generate the code in order to validate also the security requirements that are done from risk analysis. So what is added, in fact, is the part in red. On what was presented as a first security service is a part dashed in orange with the capability to work. And you may see that for the operational flow, nothing changed. In fact, you may keep your own flow. The part related to security is only added just close to it, but there's no change of current design flow. Okay, so I talked on the secured functional chain. So as I designed a tool, I have to define what is a meta model in order to express some instances of this meta model to define or to set a secret functional chain, which is the part presented in blue on red. The part in blue, in fact, it is a functional chain currently existing in Capella. What has been added for security purpose is indicated in red, related to secure enclave, confidentiality, and type of the functions. So in the tool, we have two capabilities to express security functional chains as inputs, as a standalone secure functional chain, or we can also use Capella tools, Capella Designs. That is what I will show in this presentation. So in the part of right, there are three parts. It is a proof of concept. On the it is possible to show the description in secure functional chains as some kind of security analysis. We'll give elements, but don't go in details, and realize some kind of analysis results. Okay, for the part related to Capella, so we proceed to a model transformation to instances of Capella models using the Capella meta models, two instances of the securized functional chain meta model. So people experts in Capella meta model should find elements related to functional chains at physical level on the top left descriptions of meta models. Okay, so I have as entries this kind of modelings with annotations. We generate the underlying securized functional chain, which is represented in the middle part, the middle diagrams. You may see that channels are also considered as components, like air transit, for example. And with this secure functional chain, we may proceed some analysis, which defines at which state, which on the functional chain, we may compute some signature, some ciphering, and also deciphering, to compute some integrity control after signature computations, and to define and to detect some kind of lags in terms of confidentiality protection. Okay, I have a very short demo that presents what was shown there. So finally you see the modelings, and just in this component you have in the summary fields the information related, and it will be interpreted. So just a few elements added, in fact. And as there may have different functional chains going through functions, the information related to a particular functional chain has to be described, in fact, in the related diagram related to a functional chain, which is presented there for one of the two functional chains. So here we have a creation. With the creation, we have the level of confidentiality. And for the other ones, if I take the other one, we have in use rights. So this element is interpreted and exploited. And I have the tool. So here we have Capella file or standalone descriptions, but I present Capella files. So there's already Capella here. I have my set of secured functional chains, which represent elements with the elements added as extra notations. Here are some a lot of prints on analysis that are done. I want to focus on the results here, and I show maybe here. Here I say that for uncompressed data deciph, it can be ciphered with compressed data, and in fact it can be ciphered in all the other ones because in fact it is in motion components. And one other element. So it is a proof of concept. It has still to be. If I take front-end RE1, for example, here the enclave confidentiality, as we've seen, it is of C1, but as there are different flows going through, which is not only on C1 but C1 and C2, it defines that the effective confidentiality is of C1 plus C2. So there will be an alert that may be raised to say, with these design choices of these flows on this particular physical modeling, the initial requirements related to the protection of a level of confidentiality of the data is not met, in fact. Okay, this is just for this very small demo. In fact, I give these elements in this slide. What we do, we have CIF, ciphered, and deciph. In fact, we label the particular function related to the secured functional chain node with a value which may be CIF or deciph or ciphered. There are other, but for this particular example, it is just CIF and ciphered. On the transmissions of this text to one another, we may define in the platform the kind of security actions that can be done. Here it is a ciphering with a level C1 of the data, and here deciphering, which after that can be exploited on the real platform to design and to express such security code to be generated. On here, as you see, as I've shown, it was C1, but we need C1 plus C2. So we may send an alert. We need for C2 protection for this particular component. So this is ongoing work. We still have a research perspective for the first security service. In fact, I said that Capella can already integrate all these features. There is just something missing. It is in terms of inconsistency analysis and capability to structure and integrate elements directly to the new iterations, even if I know their capability to compare two models with Capella. So we are ongoing working on providing such tool. And in the second point related to the security services, we state the confidentiality product line management at a system level. In fact, is a specialization of something which is more general, which is the variability of product line management. And we work to extend the tool in order to take into account the problematics and issues related to variability management, which is an interesting topic. In the security analysis of Capella Designs research elements, I show a demonstrator which has to be provided as a provision in the software artifact to a paper that is submitted, so I have to wait. If accepted, it will be provided in a Zenodo repository. But if people are interested to have access to it, just email to me. Also, I focus in this presentation on confidentiality management. In fact, integrated requirement analysis is slightly different with some extra information to be added on the different analysis to be done. So we also work on this part. We may consider that system architects may, in some cases, want to work on the integrations of patterns of known architectures of a three-tier architecture or microservices architectures that are known architectures, we may provide pre-securized architecture to be composed, because the securized functional chain have good qualities in terms of compositions and also in capabilities of hiding internal behaviors in the subsystems, which also can be interesting. I did also an assumption on what all I presented, which is I say I can sign or do some integrity control, cipher, decipher. To do that, I need to share keys, of course, between components. We are also working, we have also solutions on the key exchange provided as platform service, exploiting information related to system design. And finally, I indicate I can know what to sign, exiting a component or ciphering and decipher, arriving to another one. If I know exactly on which platform it's targeted, it is quite easy to generate the exact code to be integrated as a proxy on the operational software design. In fact, when it can be done, it does not prevent the work to be done at software design on the operational part. It can be done after taking in account information or validation related to security requirements. Now, I conclude, in fact, with the feeling I have that at first glance, we may consider that the security management of complex critical systems is a big issue for the to move from any kind of processing to the use of modeling processing flow. But in fact, we may see that the issues may be raised in terms of confidentiality management on automatic management of security requirements. And finally, these system specification on design at system level using seems to be very interesting to be used for these features using model-based system engineering. And finally, it can be I said ideal use case for the adoption of model-based system engineering in industry. So this solves my ends my presentation. Thank you for attending. If you have a question, I will answer.
Thank you very much, Michel, for your presentation. On my side, I was wondering, are you thinking with your students to transform, let's say, your proof of concept in an add-on for Capella to make it more available, or you not have plan on that?
Yes, this is possible. In fact, as it is a proof of concept, I wanted to go further directly in the algorithms. I had a knowledge on the Capella meta model at XML levels, and I didn't know if I would have enough capability of access of the information using add-on tools on access on particular elements of the meta models. What I didn't say is that, yes, the students work on research projects on what I presented at ongoing research. I want to thank them. I profit to thank them. They have courses in system engineering, modeling using Capella, on cybersecurity, because it is the topic of the engineering school. So if you have internships or job proposals, do not hesitate to send them to me or to the particular service for these very good engineers. And I think it is to leverage in terms of maturity. So with some help, I'm not a specialist in the tools of the integrations of into the Capella's add-ons on Sirius, on all these elements, but that could be done in the future.